Welcome to Identifying Outliers. After completing this lesson, we should be able to compute the inverse of covariance matrix given a dataset, compute the Mahalanobis distance for all elements in a dataset, and remove outliers from a dataset. The Mahalanobis distance is a multidimensional generalization of measuring how many standard deviations a point is away from the mean. It is measured along each principal component axis and takes into account the correlations of the dataset. It is a unitless and scale-invariant distance, which can be used to detect outliers. Let's start with an example of an outlier. I use the same DFVEC data frame from the previous two lessons, which is a 10 rows data frame with 2 columns, ID and features, each feature being a vector of size 3 with randomly generated values. Here we've used the vector assembler to turn these 3 columns of randomly generated values into a single column in a data frame, where each element is a vector with 3 elements. Then I append a new vector that is an outlier. All its values are 3, much greater than the other vectors in the data frame. The resulting data frame, as shown in its last 5 rows, presented in descending order, look like this. Now I standardize the data frame using the standard scalar introduced in the previous lesson. This is an important step when computing Mahalanobis distances, since its computation relies on the covariance matrix. So if I standardize the feature vectors to 0 mean and unit standard deviation, the covariance matrix is exactly the same as the correlation matrix. And the correlation matrix has an implemented method on the statistics object, which I'm going to use soon. Back to the standardization. I do exactly the same as before when I introduce the standard scalar. I create an instance of it, set its input and output columns, and set with standard deviation and with mean parameters to be true, since I want the features to have 0 mean and unit standard deviation. Next, I fit the standard scalar model using my data frame and then transform the data frame using the model. The resulting data frame, as shown in the last 3 rows, presented in descending order, look like this. It's time to compute the inverse of the covariance matrix. Since my feature vectors are already standardized, the covariance matrix is identical to the correlation matrix. Data frames only provide methods for the computation of correlation or covariance between 2 columns at a time. But the statistics object can compute the entire correlation matrix over an RDD of vectors. So let's proceed. After doing the appropriate imports in this case, the Breeze library is needed for computing matrix inversion. I obtain an RDD of vectors from my data frame, selecting only the column feature vectors, accessing its RDD attributes, and then mapping each feature vector into an MLlib vector. Next, I use the statistics object to compute the correlation matrix for the feature vectors. Remember that correlation and covariance are the same here in the case of standardized features. The result is shown as col covariance, col-cov. Then I need to compute its inverse. I create a new instance of a 3x3 dense matrix from Breeze and then call the inverse method to get the inverted matrix as a result, which I assign to inv_col_cov_b. Now to the Mahalanobis distance computation itself. First, I create a user-defined function, a UDF, which takes a column of MLlib vectors and outputs a column of doubles. For each MLlib vector v, my function creates a Breeze's dense vector vb and uses this new vector in the Mahalanobis distance formula. That is, vb's transpose multiplied by the inverse of the covariance matrix multiplied again by vb. The result is a double value representing the computed distance. Having defined the user-defined function for the Mahalanobis distance, I have to apply it over the column of feature vectors in my data frame, the scaled feet column. I use with column to perform this operation The resulting data frame is then named DF mehalanobis. And the result looks like this. Notice that the outlier I've added has an ID number equal to 10. Its mehalanobis distance is not surprisingly the largest in the data frame. It can be argued that the second largest distance in the row, with ID equals 2, is also an outlier. It is possible to define a threshold over which points are considered outliers. Another approach would be to consider as outliers points in the 99th percentile regarding its mehalanobis distance. In this example with only 11 rows, I choose to consider the points with the top 2 computed distances as outliers, as shown in the slide. Having defined a criteria, the next step is to remove the outliers from the data frame. I start by selecting only IDs and distances from my data frame, and then sort them by distance in decreasing order. Since I'm only interested in selecting the IDs of the rows to be removed, I drop the distance column and collect the result as shown in IDS, which is an array of rows. Every row has only one element, which is known to be a long-typed ID. So I cast each element to long and then use slice to get only the first 2. These are the IDs of the outliers, in this case 10 and 2, as shown in ID outliers. Now that I have the IDs for the outliers, I can just filter them out by keeping everything that is not an outlier. Then the resulting data frame looks like this. Points with IDs 6 and 10 are gone. Notice that even if I have standardized the feature vectors before to ease the computation of the covariance matrix, now that the outliers have been removed, it is necessary to standardize the feature vectors once again. Having completed this lesson, you should now be able to compute the inverse of a covariance matrix given a dataset, compute the mehalanobis distances for all elements in a dataset, and remove outliers from a dataset.